Good afternoon, everyone. This afternoon, we are very happy to have Jean-Luc Lehners to tell us about his work on circuit complexity of primordial perturbations. So please take it away, Jean-Luc.
Thank you, Dongsheng. Thank you very much for the invitation to give a talk here in your series of talks. I'm going to talk about something which, in fact, is largely based on works that were done in the quantum information group. So I think it's pretty appropriate that I should give this talk here. I should say that this is all work done together with Jérôme Quintin, who is also at the AEI. And we published a paper in December with these results. So, okay, so what is this about? So the thing is that we know from, for example, from the Planck data that the early universe had a radiation background with small temperature fluctuations in it, and from the very nature of how it's measured, we know that these are classical perturbations. So these temperature fluctuations are classical temperature fluctuations. Nevertheless, in most theories which try to explain the origin of these fluctuations, they arise ultimately from quantum fluctuations. So there must have been a process by which these quantum perturbations were turned into classical perturbations. But because at the origin they were quantum perturbations, you may ask, how can we characterize these quantum perturbations? And a way in which has recently become prominent has been to try and see to what extent one can equate the processes that made these perturbations with a quantum computer. In particular, you can ask the question, if you would simulate whatever happened to these perturbations, if you would simulate this by building a quantum computer, how complicated would this quantum computer have to be? In particular, how big would it have to be? How many gates would it require in order to achieve the same end result? And the thing that Jérôme and I wanted to find out about in this work was to see if different models of the early universe have different characteristics in this respect. So the idea is that, one starts with a quantum state for the perturbations, one puts it through a kind of a complicated machine, and at the end of the day, you have the CMB coming out. And the question is just, how complicated does this machine have to be? So let me just review the notion of circuit complexity. Although I think most people in this audience are very familiar with it, so I can go a bit faster. But if something is not clear, please ask. Now, the simplest setting in which one can analyze this is by looking at Gaussian states, which is in fact all we will need here, because the primordial perturbations are Gaussian to a very good approximation. And so we will start with a reference state here with frequency little omega, and a target state with frequency capital omega. Since this is a quantum system, the evolution is unitary, and there's a unitary transformation which takes the reference state to the target state. Now, the idea of complexity is to see how complicated does this unitary transformation have to be, of how many elementary operations does it have to be composed. And by elementary operations, I mean something like the following examples. There are these operators here, h, j, and q, which have certain sort of elementary effects on the wave function psi. For instance, here h just gives a phase change in psi, whereas j, which is given by the momentum operator, shifts the position x by an amount epsilon. This operator q here, which is composed of both x and the momentum px, has the effect of actually rescaling the coordinate x. So a general circuit would be composed of any number of such operations in some random succession. But you can then imagine that, of course, a general circuit would have operations which would partly undo what earlier operations already did. Now, we're not interested in that. What we want to know is what is the shortest quantum circuit that would take us from the reference state to the target state. Okay, in the example that I was just giving here, in fact, this gate Q would be sufficient because this rescaling of X is exactly what one needs in order to go from the target to the from the reference to the target state. Sorry. Now, in fact, here you can see if you make a circuit now which is made of alpha copies of Q, it changes the frequency by this amount e to the 2 alpha epsilon, and so in fact, you get the required transformation if 2 alpha epsilon is precisely given by the logarithm of the ratio of the frequencies. Now, the complexity can then be, the idea of complexity is to say we want this to be the number of gates. So in fact, normally you would say, you would take alpha to be this complexity, but we want to have a good limit as epsilon goes to 0. So one rescales this by epsilon to obtain a finite limit when epsilon goes to 0. And the complexity then is just given essentially by the logarithm of the ratio of frequencies. And I should say that, that many of these ideas were worked out by Rowe, who was a postdoc in the quantum information group, together with Rob Myers. Now, the main thing about complexity for us here is that really it's, we can see that this is a logarithmic quantity. So small changes in the complexity actually correspond to rather significant changes in the wave function. Now in cosmology, these frequencies are typically complex numbers. And so one has to undertake a generalization of what I just showed. Now a simple generalization would be just to analytically continue the formula which we had. And this has been pursued by a number of authors. And as I will explain in a little bit, we thought that this was not the best generalization, and we think that there is a better way of characterizing wave functions which have complex frequencies. Now, this this method which we used is based on Nielsen's geometric method, by which you actually you equip the space of circuits with a metric, and in this space, then the shortest circuit corresponds to a geodesic, and then of course you can use differential geometry to find the complexity, because this is then a very powerful way of finding geodesics, and the geodesic will give you the complexity. This again here we will follow works by Michal and Hugo and Rowe and collaborators, and this is now based actually on working not directly with a wave function, but rather with quadratic combinations of position and momenta. Okay, because since we are talking about Gaussian states, all of the information is in quadratic combinations. So if we group together position and momentum as psi, then and we look at expectations values of psi, of two psi's, then you see we can decompose this into a symmetric and an anti-symmetric part. Now, the anti-symmetric part, you see this comes from xp minus px. This just expresses the canonical commutation relations of quantum mechanics. So this is just a fixed matrix omega, and a fixed anti-symmetric matrix. And so then, in fact, all of the information is in the covariance matrix G here. And this covariance matrix is given by the expectations values of x squared, p squared, and also xp plus px. Okay, if we have a target wave function, which I write like this, as e to the minus half a plus ib x squared. So the frequency is divided into a real part A and an imaginary part B, then one can immediately calculate these expectation values. And for instance, one can see that 2 times the expectation value. The evolution equation in terms of covariance matrices then is given by this formula here, that the target covariance matrix is given by U times the reference matrix times the transpose of U. Okay. Now, as is well known in standard quantum mechanics, you can now perform certain transformations on the position and momenta vectors, and if these transformations belong to the group SP2, then they leave the canonical commutation relations invariant. This suggests that it is useful to actually look at the algebra SP2, and in fact, this algebra is generated by quadratic combinations of X and P. So here we call them V, W, and Z, and these combinations actually satisfy the algebra of SP2. Now, what Hugo, Michal, and collaborators had realized is that for the kind of states that we're looking at, in fact, even a subalgebra is enough. And one can take, for example, the subalgebra spanned by V and W. So we just have two types of elementary operations, or quantum gates, if you like, which are just given here by V and W, or by the, or rather by the exponentials of these matrices. Now, moreover, there's one more simplification we can do, which is we can use a squeezing operation with S being given by this diagonal matrix to just bring the reference state to unity. And then we likewise transform the target covariance matrix. And so, instead of going from the reference state with frequency little omega to the target state, we can, in this way, go from the unit matrix to these transformed target states. And the distance will be the same. This is like just simply a shift in measuring distances. This is like a shift of coordinates in measuring distances. Now, okay, so now how do we get geometry into this? Now, the idea is that we will represent a circuit by a path where you can think of this path being parameterized by S tilde here. The MIs are the gates which we use. So these are these V and W matrices that I had on the previous slide. And the Ys here you can think of as the switches, which, they could be 1 or 0. They could say that a certain gate is turned on or turned off. Right? So if you follow this circuit from 0 to little s, this circuit will be a path, and it will show you which gates are used along this particular path. And if you just write out what such a path typically looks like, one can see that the general element of this this circuit is given by a matrix of the following form. So it has two free parameters, Z and Y, and it's essentially a matrix in which the upper right triangular part is, well, it's a triangular matrix with one entry being 0, and that's sufficient to actually deal with Gaussian states with complex frequencies. Okay. Now one can invert the definition of the path up here to get an expression for these switches Yi, and these switches really are like the basic coordinates on the manifold which we want to look at. And then so out of these one can just form a metric, and with a simple choice of Gij, one just gets the metric which is the metric on the hyperbolic plane. Now one could choose different metrics Gij here, and having such different metrics would allow one, for example, to penalize certain directions. So if you want to say that a certain gate costs more, then you would prefer to have a quantum circuit which would, use fewer of such gates. You could implement this by letting this particular metric entry be larger, and so to have a higher cost associated with going in this direction. Okay, so in that sense, there is also some arbitrariness in choosing a certain metric, but here we are using this simple choice, which moreover has the particular property that it just gives us the hyperbolic half plane as being the space on which these quantum circuits live. Now, the fact that it's the hyperbolic half plane makes certain things very simple, because, for instance, we know what geodesics are in this geometry. They are given by arcs of circles that are perpendicular to the boundary at z equals 0. So if you recall, the metric has a 1 over z squared, so it only makes sense to look at this metric in, when z is either chosen to be always positive or negative. Here it's chosen to be positive. And so z equals 0 is the boundary of the hyperbolic plane. And in fact, our reference state, the identity covariance matrix, is just given by the point 0, 1. That's the reference state. And the target state is given in terms of these numbers that characterize the frequency of the target state. Okay. And so you then a geodesics, so an optimal circuit which would take us from the reference to the target state would just be given by such a geodesic, such as an arc of a circle in this space. Moreover, because this is hyperbolic geometry, we have a straightforward formula for this distance. And the complexity then is just given by the distance. The distance is just given by the inverse cosh of this quantity x, and x is essentially the trace of the covariance matrix. Okay, the formula is, is straightforward enough, but there's also a useful rewriting of this formula, which is given in terms of the logarithm of this quantity x plus square root of x squared minus 1. So here again, you see that the complexity really is logarithmic in the change in the in frequency. Now, there's from hyperbolic geometry, we also know that there's a useful way of depicting the hyperbolic plane, which is to use this map to the Poincaré disk. So there's a simple map, which if you write a coordinate on the hyperbolic half plane, now as a complexified number, capital Z, then if you let Z go to Z minus I divided by Z plus I, you take the upper half plane to this unit disk. And in this unit disk, now the reference state is right in the middle, and the target state turns out to be somewhere near the boundary of the Poincaré disk. And then, in fact, the shortest distance will again, shortest distances on the Poincaré disk are again arcs of circles that are perpendicular to the boundary. But from the reference state at the center, it will just be a straight line towards the target state. So now we can ask, in cosmology, what would we actually expect the wave function to do? What would we expect it to behave like? And so the way we wrote it earlier was this exponential form with A, the real part of the frequency, and B, the imaginary part. Now, also we saw earlier that the amplitude, the expectation value of the amplitude squared is 1 over 2A. So if we want these quantum perturbations to be amplified and to turn into large perturbations, which we have a chance of seeing on the sky, we need the little a to become small. Okay, so this is one thing that we expect to happen. The other thing that we expect to happen is that the wave function should become classical in a WKB sense, because of course we know that the perturbations that we see are appear to us as classical perturbations. And for this to happen, what one needs is that the phase changes rapidly compared to the amplitude. So B has to change fast compared to A. And this leads to what is called what is known as a squeezed state. Okay. Now, how the complexity depends on the amplification and on squeezing may be enlightening also to see. So let me give you some rough characterization of this. So we saw that the amplification essentially goes as 1 over A. So a large capital A here means a lot of amplification, and then a large squeezing means a large ratio of B over A. Now, if we put this into our formula for the complexity, we see that this formula really is sensitive both to the amplification and to the squeezing S. And that's the main reason for why this particular way of defining complexity is useful in cosmology. Now, if we go back to I said at the beginning, there was a formula complex case, but if one now writes this formula in terms of amplification and squeezing, you see it essentially goes like S squared over A squared. And so you can have a situation in which both A and S are growing, yet the complexity is doing nothing. So that's why we think that this is not an appropriate formula in the cosmological context, because in some cases, and we have found such cases, it is indeed true that this formula is not even though the wave function is changing a lot, the complexity is not evolving much at all. And so this does not seem to be an appropriate characterization. Now,
so Jean-Luc,
yes,
a question. So this formula is just based on a naive generalization, like from the ratio of real frequencies
yes,
to what happens when these frequencies are complex in the wave
yes,
function,
that's right. Mm-hmm.
So probably this formula actually is not even derivable as complexity in the Nielsen sense, right? It's just some.
I think it is, because you have to then separate real and imaginary parts into two different variables, and then I think it can be done. In fact, I think it was done in papers by these authors here. But
so basically, you're trying to say that this is a choice, and that this.
I'm saying it's a choice. Yes.
Okay.
Yeah, it seems to me that it's a choice, and when Jerome and I were analyzing this, we started using the analytically continued formula, because it's sort of it's the first thing you think of doing. But then we realized that it gave some sort of strange results, and then we came across essentially, well, basically your papers about doing this with the SP2 geometry, and this to us seems a much, in retrospect, then it appears a much more natural choice.
Thanks.
Johannes, did you have a question also?
Yes, also building up on that. So for complex frequencies, I guess there would be an issue with taking a logarithm. But do I see it correctly? You can avoid that because it's only then the absolute values of the frequencies appear there, or?
I'm sorry, I missed the first part of your question. You said?
Because if the frequencies become complex and you take a logarithm, there might be issues with what Scheele, how to take the logarithm of the complex number. But I think you can avoid that. Or...
Yeah, that's not really a problem. I think that's, yeah, I don't think that's the issue in the end. But in both cases here, one has to take a logarithm, and it's that's okay. Yeah, it was mainly this. The main problem we saw was that you might not be sensitive to the effects to the physical effects that you are actually interested in. Now, yes. So one can also show what happens on the Poincaré disk by using such an analysis, and it turns out that we start from the reference state in the center of the Poincaré disk, and amplification actually ends up being motion along this line here, the sort of horizontal line that goes through the center towards the edges, whereas squeezing is can be achieved by one of the orange lines. So either going to the right here or going around the border of the Poincaré disk. But in any case, the states which are both amplified and squeezed are just here on all the way on the right-hand side where the little yellow star is. So that's where you have to end up. Now, I will get back to this in how specific models achieve this, but so let me first present the cosmological models that we were interested in. And so, of course, one model is inflation, which is also the only model that had been studied already in the literature in this context before. And so we know that inflationary models can fit the CMB data in particular with so-called plateau models, where the potential is very flat and relatively small in magnitude. And then, of course, at some point, inflation has to end, and we have to go into some kind of minimum where the inflaton field is stuck. Now, such models, as is well known, have a very simple way of demonstrating how quantum fluctuations can turn into classical density fluctuations. And also, inflation is already taking place in the expanding history of the universe, and so there's a direct link to us today. So the whole history from inflation to today is in principle easily calculable and reliable. Now, the problems with inflation are that the initial conditions for inflation are not very well understood, because the energy scale has to be small compared to the Planck scale in order to fit data. And also there are issues with such very flat potentials, because they can lead to eternal inflation. Now, because of recent work that Jerome and I did together with Caroline Jonas at the AEI, we think that just already semi-classically eternal inflation might be ruled out. Nevertheless, there are many open questions still associated with inflation, and especially with the beginning of inflation. And that's why it also makes sense to look at alternative models. Now, in terms of just fit to the data, you see the typical predictions of inflation are that you have a spectrum that is close to scale invariant. The deviations are of order epsilon, where epsilon is the equation of state, or the slow roll parameter during inflation. Non-Gaussianities are typically very small, because the inflaton self-interactions are very small. And in simple models, there's also a direct link between gravitational waves that are produced by inflation and the temperature fluctuations. Now, if you compare this to the data, now the spectrum is very highly consistent with the data. Also, non-Gaussianities have not been observed yet, so this is very consistent. However, there's some tension due to the fact that gravitational waves have not been seen that primordial gravitational waves have not been seen, because in simple models of inflation, they would be expected to be there. Now, an alternative model that we've been interested in is that of Ekpyrotic cosmology, where you imagine that there was a contracting phase before the current expanding phase, and that in this contracting phase, the universe was contracting very slowly, and this also has the effect of making the universe very flat. Then you have to imagine that the evolution is followed by a bounce from the contracting phase into the expanding phase. And many models for such bounces have been studied in recent years. Now, I should say that what is nice about these models is that the universe is, the smoothing phase is under very good control, because the Hubble rate is very low. The universe is shrinking very slowly. So there is no runaway, as for example, in eternal inflation. There's nothing equivalent to that. Also, dark energy, in cyclic extensions of these models, dark energy has a natural role because it helps in stabilizing the cycles. And so actually one can see this as a nice feature, because dark energy otherwise appears to be somewhat unnecessary. Now, however, what is the big open question in these models are the bounces, right? Because even though effective models of bounces can be constructed, it is not clear to what extent they are really allowed in fundamental physics. This is a big open question. Now, I should also say that Ekpyrotic models are a little more complicated in terms of generating the required temperature perturbations, because they need two scalar fields in order to do this. The way that it works is that, in fact, the field which corresponds to perturbations of the Ekpyrotic scalar itself, that field does not really lead to observable perturbations. It does not get its quantum perturbations do not get amplified. But if you have a second field, which you can picture as being in a transverse direction, this does get amplified, and moreover, it can obtain nearly scale invariant perturbations. Now, in these models, typically, one can again obtain a nearly scale invariant spectrum of perturbations, but the self-interactions of these scalars are automatically quite large, because the potential needs to be quite steep. And so the non-Gaussianities are typically fairly big, but because the universe is contracting very slowly, the metric is changing very little, and so gravitational waves are not produced at all. Okay, so in this case, the spectrum is consistent with observations, and the non-detection of primordial gravitational waves is consistent, but there is some tension because really one should see non-Gaussian corrections very soon, or maybe one should already have seen them. There exists a variant of these models in which you use a non-minimal coupling between two scalar fields. And this is in such, in this variant, I will not talk about it much, but let me just say that the main advantage is that in such models, the non-Gaussianities can be very small. So you can fix this feature or bug that the non-Gaussianities are typically large in Ekpyrotic models. In this particular type of model, which however requires some tuning, I should say, the non-Gaussianities can be small. Now, another model that we're looking at as sort of a contrasting model is simply a contracting phase with matter domination. So if you just have ordinary matter or just any pressure-free matter in a contracting universe, this also leads to a scale invariant spectrum of perturbations. The reason why this is not discussed so much in cosmology is that such a phase is actually unstable. So you need very special initial conditions in order to get such a phase. Moreover, in the simplest incarnation of these models, the tensor to scalar ratio is much too large to be in agreement with observations. But you can construct more elaborate models in which you can avoid this, and where the primordial gravitational waves that are produced have a much smaller amplitude. Now, in all of these models, we would like to now calculate the wave function of the perturbations in order to see in order to be able to characterize their complexity. Now, I should say that this is a completely standard calculation, with the exception that normally this calculation is done in the Heisenberg picture. I mean, in all lecture notes on inflation, this calculation is done in the Heisenberg picture. Whereas, because we want to work directly with the wave function, it's more useful for us to do this calculation in the Schrödinger picture. That's why I will very briefly review this calculation here. But as I said, the calculation itself is rather standard. Just the rewriting in terms of the Schrödinger picture is perhaps a little less familiar. So let me just show you briefly how this calculation is done. If one look now, and I will just illustrate this with the co-moving curvature perturbation, which is a gauge invariant variable, which is useful in characterizing primordial perturbations. Now, this curvature perturbation has a very simple action at quadratic order. Basically, it's just like a massless scalar field in the early universe. Now, since we want to quantize this field, one normally does a transformation to conformal time and to a rescaled variable v, the Mukhanov-Sasaki variable, precisely such that the action becomes canonically normalized, and then we know how to quantize it. Okay, so if we do this rewriting, that's the action we obtain here in terms of v, and then one would proceed by just quantizing going to Fourier space and quantizing the Fourier modes in just the standard way. So you introduce annihilation and creation operators A and A dagger. You impose standard commutation relations, and there's also a normalization condition which ensures that the quantized modes have the appropriate norm. And of course, they have to satisfy the equation of motion, which is given down here. Now, if we want to go to the Schrödinger picture, we would say that we would look at the vacuum state, which is annihilated by the annihilation operator A hat. Now, the thing is that one can rewrite A hat in terms of the field and its momentum pi, and then use the standard identification of momentum being given by minus I times derivative with respect to the field amplitude. If you then, this gives a differential equation for this wave function psi, which you can immediately solve with a Gaussian ansatz. where A is the correlator. And the correlator is given in terms of the mode functions f and in terms of the background evolution little z. So I didn't say what z was. Z was a combination of A and the equation of state, or slow roll parameter, if you like, epsilon. But so I should say in inflation, this is the slow roll parameter. In other models, this parameter can be big because it, for instance, in Ekpyrotic models, we have fast roll, so epsilon would be large rather than small. And so one can get the wave function, if one has the wave function for the mode functions V, one can immediately also get it for the rescaled physical co-moving curvature perturbation R. Simply by having a factor of this, inserting a factor of z squared. Okay. Now, what's very useful is that when the equation of motion epsilon is constant, then one can solve all of these equations analytically. So that's the case we will look at. So if epsilon is constant, then in fact, the scale factor just evolves as the conformal time tau to some power, 1 over epsilon minus 1. And then also the perturbation mode functions are solved simply in terms of Hankel functions with index alpha, where alpha is also given in terms of the slow roll or fast roll parameter epsilon. In general, I would just call it the equation of state epsilon, okay, because it is directly related to the equation of state. Now, since we have these analytic expressions, we can then just either plot these numerically, but since we have the analytic expression in terms of Hankel functions, we can also very easily find approximations at late times, for instance. So let me just show you what one gets by just performing such approximations. And also another thing is here, Jerome and I were mostly looking at the correlators for the physical co-moving curvature perturbation, not for the rescaled mode functions, because it's the physical perturbations which are actually then seen in the CMB. That's what we measure. Now, at late times, so in inflation, you see the correlator becomes, the real part of the correlator becomes constant. The amplitude goes to a constant. What this means is, in fact, the perturbations have been amplified, but then they become constant. And this reflects the fact that on very large scales, when the modes have exited the cosmological horizon, they freeze. They just, they don't evolve anymore in terms of the amplitude. However, the phase still varies a lot. So this conformal time tau is going towards 0. So it goes from -infinity to 0. And so you see that actually the phase grows faster and faster, which is exactly what you want in order to have a WKB classicality condition being fulfilled. Right? So this correlator becomes more and more of WKB form. And so the perturbations indeed become more and more classical. Now, if we look at these transverse modes during ekpyrosis, so the modes which are necessary, which are amplified during ekpyrosis, then actually we see a very different behavior. So here, the amplitude keeps growing, so the real part keeps getting smaller and smaller. But so here's the approximate expression. Here it goes like tau squared, and tau is going towards 0. So in fact, the amplitude grows and grows until the ekpyrotic phase ends. This means that in ekpyrotic models, the timing of when this phase ends is important, because this is what's necessary to reach the required level of amplification. And moreover, the phase of the wave function keeps growing fast. Okay, so again, we find that this turns into a highly squeezed state. If we look at the matter contraction, we find another time dependence yet again, where now both the real and imaginary parts are shrinking. However, you see the ratio of the imaginary to the real part still goes as 1 over tau and keeps growing fast. So the WKB condition is again satisfied, but in a very different manner. All this is just to illustrate that in all of these models, the evolution of the perturbations is quite different. even though they have to achieve the same end state. So now we can go back to this illustration in terms of the Poincaré disk and see what happens to the perturbations on this disk. And so here are the results. So we're plotting, here we are plotting the evolution for different early universe models. And we're always plotting the time range around horizon exit. So when the cosmological, when the mode is goes from sub-horizon in blue to super-horizon in red. And sort of at the transition between green and yellow is exactly when the horizon is reached. We always start in the center. So for inflation here, we start in the center. What one can see here is that for inflation, the modes are first amplified. I was just, let me go back here for a second. You see amplification is either to the left or to the right, but squeezing is essentially either to the right or around the border. So if I go back to these plots here, in inflation, you see the modes are first amplified, and then after they've been amplified, they're being squeezed. You go around the border and you end up here on the right as you have to. But you see that they are only being really squeezed after they already exited the horizon, whereas they're already amplified before horizon exit.
So, sorry, Jean-Luc, can I have a question?
Sure.
So just to understand what you're showing, so you're basically looking at where you are on this Poincaré disk representing SL2R in terms of time evolution of perturbations, right? So like you're just following the, okay, good. Thanks.
Yes. Starting from the vacuum state, the Bunch-Davies vacuum state here at the center of the disk. And, you know, of course, we're doing this for a particular Fourier mode, but they are all behaving in the same way. And it's just to illustrate how the process of generating these perturbations is different in different models. So, yeah, for inflation, really sort of amplification and squeezing happen in succession. The relevant modes during the Ekpyrotic phase are shown here on the upper right disk. And you see here, it's very different. Here, both amplification and squeezing occur together. And moreover, they're pretty fast. So you see we've already reached this target state, which is both amplified and squeezed around horizon exit. And what's interesting is that in a matter contraction phase, everything is even faster. So, you know, when you're still sub-horizon, so even before the modes exit the horizon, they've already been both amplified and squeezed to a significant extent. Of course, now, you know, you don't see it on this plot, they still go ever closer to the boundary as they exit the horizon and become super horizon. But this shows that, in fact, the evolution in these models is really quite different. The other two disks, you can ignore them for this talk. I'm not going to talk about these models now. So now we can look at the complexity given these results. And again, since we have the analytic expressions for the correlators, we can just also, in the same way, directly find analytic expressions for the complexity. However, they're a bit complicated to write out in full, but there are useful approximations that one can do. Now, one thing that's important that we realized is that really the number of e-folds is the appropriate time variable to use here. If you express the complexity in terms of just ordinary physical time, it varies very substantially, and it's not very enlightening in a certain sense. But you see, what we know that in all of these models, the number of e-folds, in order to be compatible with observations, and for instance to resolve some of the early universe puzzles that we have, the number of e-folds needs to be at least 60 or approximately 60 or more. So expressing the complexity in terms of number of e-folds is useful. And moreover, that's another thing, is that the expressions are very simple in terms of the number of e-folds. So for instance, for inflation, the growth of complexity is directly proportional to the number of e-folds, and the coefficient is just essentially square root of 2. By the way, this square root of 2, I did not explain where it comes from, so I should do this. In these cosmological models, you should think of the perturbations being pair created. So because of momentum conservation, when these perturbations are created, you create one with momentum k and one with momentum minus k in the opposite direction, right? So because you have to conserve momentum. So there's always two modes that come together, and if you sum over these two modes, you get, in fact, there's a square root in the definition of the complexity, and then so that's where this factor of square root of 2 comes from. So apart from that, you see the growth of complexity is just given by the number of e-folds. Epsilon is the slow road parameter, so this would be a very small number, and just a small deviation for inflationary models. Inflation here on this graph is shown by the sort of light pink curve, and what's also indicated here, so this is again as a function of the number of e-folds, and these dotted lines show that the moments of horizon exit for the various models. For inflation, this would be this line here, which is essentially coincident with the orange one. Okay, now in the Ekpyrotic case, this would be the green line here. We see that the growth of complexity is higher, is larger. You know, it's essentially twice the growth that we had in inflation. Again, it's just given in terms of the directly proportional to the number of e-folds, and there's a mild dependence on the equation of state. You see, in this case, epsilon is a large number, so this ratio again is very close to 1.
Jean-Luc?
Yes?
Can I have a question?
Sure.
Yeah. So let me look at the curve. So like for the Ekpyrosis isocurvature and also for matter domination, there is a change in the slope
Yes.
at the horizon exit. Like, is it
That's
easy
right.
to understand?
Yes. So the approximate formulae which I'm giving here are for after horizon exit.
I see.
There are analogous formulae for before horizon exit, but for inflation, in fact, there's almost no change before and after. And but for ekpyrosis, there's a big change, right? Because there's essentially no growth before horizon exit, and pretty much the entire growth is after horizon exit. So this is a clear difference between these models.
And how to understand the periods where there's no growth of complexity? So that's for the adiabatic ekpyrosis, like initially, and for
the adiabatic ekpyrosis, this is a different model which I did not discuss. Essentially, this is a model where perturbations are amplified and then the process stops. So that's why there's also then a stop in the complexity. But it's a very particular model which I took this graph from our paper where we also discussed this model, but I did not want to discuss it in the talk because it's a rather speculative model, which even more speculative than the others. So
basically the idea is that like when these curves are flat, then basically nothing really happens for an extended period of time. Okay.
Yes,
it's not that like you. Okay.
Yeah, when the curves are flat, the wave function has essentially frozen, or it's not evolving much. But this is what's interesting is that in all these cases, even when the perturbations have exited the horizon, and they, for instance, for inflation, the perturbations then freeze. Nevertheless, the complexity keeps growing because the phase of the wave function keeps changing more and more rapidly, and this is necessary for the classicality or for the classicalization of these modes. So even though the amplitude has frozen, the complexity actually keeps growing, and this is appropriate because the wave function is still changing significantly. Okay, and then if we now go to the matter contraction model, in this model, actually, the growth of complexity is the fastest. And this is, it's not, so there's it's 3 times as fast as during inflation. We don't exactly know why. One speculation is that this is a highly unstable background evolution. So maybe this instability causes the complexity to grow faster. But really, the main thing which we found from this is that, you see, okay, let me point out there are some surprising features, I would say. The first surprising feature is that the complexity seems to depend almost entirely on the number of e-folds. right? So this is, so just on how long these phases last, there's very little difference within a given class of models. So you see in inflation, the slow roll parameter epsilon changes the result very little. In ekpyrosis, the fast roll parameter epsilon now changes the result very little. So within each class of models, the complexity is essentially the same. But there is a clear distinction between classes of models in terms of the proportion, the coefficient in front of the number of e-folds, right? So in a sense, you would be 1, 2, 3 for these three different models in terms of how fast the complexity is rising. And this is very surprising to me that there is, there's no dependence on the wave number. There's no dependence on how big the potential is. There are so many things which go into building these models. The complexity turns out to be surprisingly simple. But it serves as a useful way of characterizing different classes of models, because there is a real difference in terms of these coefficients, in terms of just different classes of models.
Jean-Luc?
Yes.
Can I ask a question?
Yes, sure.
So one of the main assumptions is that you're looking at the Gaussian part of the perturbations in all these models, right? You're making a Gaussian approximation.
That's right.
So could you please remind us for which models you expect the non-Gaussianities to be more important, and that would likely alter this late time behavior for the complexities?
Now, the thing is that, yes, so you see our observations of the CMB show that the primordial perturbations were Gaussian to a very high degree.
Right.
Now, the amplitude of primordial perturbations was something like, the temperature fluctuations were about 1 part in 10 to the 4 or 10 to the 5. And the non-Gaussian corrections would come at the next order, right? Mm-hmm. So they would be proportional essentially to the perturbation squared. So when I was talking about these coefficients F and L, which is the standard way of denoting the non-Gaussianity coefficient, this is the coefficient of the curve of the perturbation squared. So you have to think of the leading term being 10 to the minus 5, say. The next term is of order 10 to the minus 10 with this coefficient, and the bounds on this coefficient, for example, for local non-Gaussianity, I can say in a moment what that is that it is at most 5. So this would be 5 times 10 to the minus 10 compared to the perturbation, which is of size 10 to the minus 5.
I see.
Okay, so even if the non-Gaussianity is detected in the near future, it will still be extremely small.
I see.
So really, these observational bounds are very strong. When I say large non-Gaussianity, I mean large coefficient of the perturbation squared, but in terms of overall magnitude, this is still a very small correction. Now, in terms of for these models, clearly it's in Ekpyrotic models where one would expect the biggest change, because these models necessarily have strong self-interactions of the scalar field that drives this phase. Uh-huh. And so that's why typically in these models the non-Gaussianities come out much bigger than, say, for example, for inflation. In inflation, you see the potential is necessarily very flat. And that means that the self-interactions will be very small. It's almost like a free field, the inflaton field. So I think there would be some corrections from non-Gaussianities, and it would be interesting to work them out. But I do not expect them to be really all that big. Right.
Right.
I might be maybe wrong about this, but because I don't know if maybe complexity. Well, okay, let's put it this way. Surely one can also find a measure of complexity which would be highly sensitive to non-Gaussian corrections. And then this might be a useful way of characterizing non-Gaussianity.
Right. I mean, just simply because of the way that you're measuring complexity using these the symplectic group, it heavily relies on the fact that you're looking at Gaussian wave function, right?
That's right. That's right. Yes.
But then the expectation, what you're saying is that you don't expect the dependence on the e-fold of complexity to change substantially if you were to consider, for example, non-Gaussianities. Okay.
No,
okay.
No. and especially because of what I said, because it even the depends on something which normally has a much bigger effect, which is the equation of state. Even that dependence is very mild.
Right, right.
So,
okay,
yeah.
Thank you.
That's why, I think it would be interesting to work it out, but and it would have to go beyond the current framework, right? Because as you say, this is really based on the assumption that we are dealing with Gaussian wave functions. But yeah.
Okay.
So in fact, I've I think I've said most of these conclusions of our work, which are that the complexity is sort of a useful way of classifying models and classes of models, rather than small differences within a given class of model. And you see that the complexity is sort of, to some extent, maybe almost an oversimplification. But I think, for instance, also this way of representing the evolution of perturbations on the Poincaré disk is a nice way of highlighting really how different these models are, and how they generate perturbations in very different manners. Now, by the way, I came across this quote just a couple of days ago, a quote from Dirac, which I didn't know before, and I thought it would be appropriate to show it here. So let me just briefly read it. So he said, this was in 1939. He said, with a new cosmology, by which he means the Big Bang cosmology, with a new cosmology, the universe must have been started off in some very simple way. What then becomes of the initial conditions required by dynamical theory? Plainly, there cannot be any, or they must be trivial. We are left in a situation which would be untenable with the old mechanics. If the universe was simply the motion which follows from a given scheme of equations of motion with trivial initial conditions, it could not contain the complexity we observe. Quantum mechanics provides an escape from the difficulty. It enables us to ascribe the complexity to the quantum jumps lying outside the scheme of equations of motion. The quantum jumps now form the uncalculable part of natural phenomena to replace the initial conditions of the old mechanistic view. So this is pretty amazing, I thought. So he said that, basically you have no initial conditions, and just the fact that you have quantum fluctuations should be enough to explain all the complexity in the universe. So this is, essentially what the current picture now is, with the exception that, in fact, complexity is calculable. Nevertheless, what is missing is, even though this is calculable, there is, in a sense, no real principle that says what is preferable now. Is it better, for instance, to have an early universe model that has very small complexity, or is it better to have one which has large complexity? It's in a sense just a different characterization of these models. It's not clear to me which one should be preferable. Also, one thing I should say is that in the work that we've done here, we have just characterized the perturbations, but there should be, in a sense, complexity associated with the background itself. Here we just assumed the different backgrounds, and so we don't, I think that there should be, be nice to find a way of sort of incorporating the complexity of the background as well. And finally, one thing that I did not mention so much, but there is, in a sense, also a strong sensitivity on initial conditions. You see, in some of the models, the complexity is sensitive to the number of e-folds of the total evolution. So if a certain phase lasted for a very long time before the currently observable modes were produced, in principle, this measure is sensitive to that whole prior evolution. And so in a sense, the way in which these early universe models started is crucial for the end result. And I think so it would be very interesting to see what the impact would be of potential prior phases of evolution before the models started that I was talking about. Okay, I think that's it. Thank you very much for listening.
Thanks a lot for this very nice talk and the good time control. Maybe we can take a few questions.
So I do have a question, a comment, Jean-Luc.
Yes.
So can you go back, please, to the previous transparency where you had like this master plot, I think? Oh no! Oh yeah, this one. Yeah. So just to understand, because I think I don't understand it fully. So you have different momentum modes, right? For which you calculate correlation functions, right?
Different. Well, the momentum here is fixed. We look at one Fourier mode.
So you look at the one Fourier mode, and did you look at how this changes with respect to Fourier mode, or like, do I remember correctly that you said that it doesn't change much?
It doesn't really. Yeah, it does not depend on the Fourier mode.
Okay.
That's one of the interesting things. This is one of the things that it does not depend on that. So this would be true for each Fourier mode. Good.
So, does it mean that the correlation functions of this for each Fourier mode are just the same, or like they don't vary much with k, or that's not correct to say? It's just that the complexity somehow loses this information.
They do, yeah, they do depend on the wave number, right? Because this is essentially the frequency of the mode, you know, when they start in their vacuum. But the complexity is sensitive to the change in the wave function.
Okay.
Right, so they all change in the same way. That's what this is. That's what this is saying.
Okay. I see. Okay, that's very good. And then I have a question about the plot that you're showing, right?
Mm-hmm.
And I'm not sure I understand it in the end, right? So basically, n is a time variable, right? It's some way to parameterize time evolution, right? In the problem.
Yeah. So in fact, n is I think I didn't say it. It's given by the change in a times h. So a is the scale factor, h is the Hubble rate. This is the appropriate quantity when you discuss the flatness puzzle, for instance.
Okay. So at every value of this time variable, there is a state, right? And we take as a reference state the state that was there initially, which you said was Bunch-Davies vacuum, as far as I remember, right?
Mm-hmm. Yes.
And then you know, these perturbations, you know, changing the state of the perturbations change with time, right?
Yes.
And what you do is you basically at every instance of this time variable n, you ask a question: what is the shortest circuit?
Yes.
That connects the Bunch-Davies vacuum with the state at a given time, right?
That's right. Yes.
But then I thought that at late times, the state is going to be the same for all these models, or that's not correct to say?
No, that's not. That's precisely the thing that I want to emphasize, is that the way in which these perturbations are generated is different in these different models.
I see. So you end up with a different state in the end, that's what you're saying.
Yes. So in fact, if you look at the correlators here, I gave you the late time expressions for the correlators in different models. They are very different.
I see.
Nevertheless, all of these models can produce the observed temperature fluctuations.
I see.
There is still a non-trivial step to go from this to the observed temperature fluctuations, in the sense that if you want to do it properly, you have to look really at how decoherence happens in the early universe when these perturbations now really become classical. But even without that, already there are some steps which you need to take to go from this to the actual observational consequences. So from these, an example is given by the following. So the amplitude here in inflation, for instance, is, comes from the real part of the correlator, which goes to a constant. And this constant actually does depend on the value of the potential, on the magnitude of the potential during inflation. Now, in the Ekpyrotic case, for instance, the scalar field is rolling down a steep potential, and the real part of the correlator keeps changing. And so keeps changing, and then this potential this Ekpyrotic phase has to come to an end. When it comes to an end, the potential turns off. And when this happens, so at that value, that's when the magnitude of the perturbations gets frozen in. Right, so this keeps evolving until that moment, and then the magnitude will end up being the magnitude at the minimum of the potential.
And was it the plot? Sorry, was it the curve in the other plot which was saturating the constant?
No, but you see
No.
the phase of the wave functions keeps changing.
Mm.
So that's why actually even when
but it goes to zero, right?
Sorry?
It goes to zero, right? So at some point, like it effectively does not change, right? It's very close to zero.
Sorry, then the tau is going towards zero. So actually it changes.
Oh, okay. Sorry, it changes a lot. Okay, good.
Changes more and more.
No. I see. Good.
But you should think that this will end at some finite value of tau.
I see.
In fact, then at after these models come to an end, reheating has to take place, and at that point, we stop our analysis at that point, because now you would have interactions between the scalar field driving these phases and all other matter particles that are produced, and you would presumably have to take into account decoherence that comes from all these interactions. And I think that at that point, this analysis of complexity and this formula which we're using is certainly not applicable anymore. So we're just going to the end of these phases, and that's where we stop.
So but is what you're saying is that, okay, like the whole information here is encoded in this wave function, right?
Yes.
The wave function has a real and imaginary part, and basically what you're saying is that there's a formula for complexity that is sort of sensitive to both real and imaginary part, right? Or like some rays. Yes. Okay. So basically, yeah, I mean, like that's basically the story, right? And like the rest is like trying to work it out, like how it precisely happens. Okay.
Yes, and one is the sort of the inverse of the real part is the amplification, and the ratio of imaginary to real part is the squeezing, and these two things are important for characterizing the perturbations. And the nice thing about this this SP2 formula is that it is sensitive to both of these processes.
Yeah, good. Yeah, I also have a comment, but maybe some other people want to ask questions first.
Maybe I can ask a bit in this direction. So if one would continue in time evolution towards the present time, do you see like the prospect that maybe even like experimental input could be used to do the inverse process? Like now you have shown that complexity can distinguish different models. They show different time evolution of complexity. And maybe any chance that any experimental measurement or any conclusion from present day could be used to like this, or to make a statement what model you are present in the Big Bang phase, so that one could essentially answer this question that relates to the singularity.
I have to say, I did not understand everything you said, because for some reason your connection was not always there. But I think the first part of the question at least was about the inverse problem of I would say that, whether that, in a sense at the moment, this is clearly just a theoretical tool of characterizing different models. I don't know how one could actually, for instance, measure the complexity directly. If one could somehow measure it, then of course this would be a great way of figuring out what would be, finding out what was the evolution in the early universe. The trouble about this is that, when reheating happens and the perturbations really become classical and turn into these classical density fluctuations and temperature fluctuations, a lot of the quantum information gets lost. Okay. In fact, it kind of has to, in order for the perturbations to become classical. And so, so right now, I don't know how one would go back and measure. I mean, how one would actually measure the complexity and then be able to draw conclusions about what happens. So I think that right now I see it more as a theoretical tool that is sort of a useful way of characterizing different models of the early universe, because it gives a characterization which certainly I think was not known, right? That or it was not clear in this sense that the way these different early universe models produce perturbations, that this is so different and but so different in a way which is easily characterizable, right? So I think before we did this work, I would have, if you'd asked me, I would have said, they're just all different, but I cannot tell you how they are, in what quantitative way they are different. But this is a nice way of showing just in what quantitative way early universe models treat perturbations differently. By the way, I should have said one thing before when Michal was asking me about the dependence on wave number, which is that, so what I was saying is that, you can analyze each wave number separately, but in the actual physical process of how the perturbations are generated, different wave numbers in a sense cross the horizon at different times, right? So in that sense, the complexity will be different for different wave numbers. They all evolve in the same way, but for example, if you have a model in which the only change in complexity occurs when you are super horizon, then those modes which exit early will have a much bigger complexity than those that exit late. Right? So you have to think of this as different wavelengths, cross the horizon, because they are generated at different times. So they cross the horizon at different times, and so there's a sequence of so the Fourier modes really sort of, you can think of them as being generated in a sense one after the other as a function of the wave number.
Hi, can I have some naive questions?
Sure.
So based on my impression, you have some wave function that it has a complex, like it has a kind of imaginary part that could serve as a phase for this wave function. And I used to think that when two states are differed by a phase, then somehow they should be regarded as equivalent. But in your way, it seems like states differed by a phase, actually they are not the same.
Yes, I think the important thing is that the phase keeps changing. So it's more sort of the change in the phase that's important. So for example, when you try to make a sort of a semi-classical approximation of a wave function, which is what the WKB approximation is, then it's important that the phase changes fast compared to the change in the amplitude in order to recover an approximately classical correlations between for the evolution. And so it's true that if you have a certain state and you calculate psi star psi to get a probability, the phase disappears. But nevertheless, if in order to characterize what the wave function is and under what conditions it starts becoming more classical, then it's important to keep track of the changes in the phase. Okay. And this is in fact also what the complexity is sensitive to.
Okay, I see. Maybe there is some derivative somewhere. And a second question is that since it seems to me that you have you have chosen a certain metric so that you can see the difference between the different cosmological cosmological models, but like supposing that I think the choice is not unique, right?
Yes.
Supposing you choose some other metric, I think for the Lie group, for example, you can choose the Killing metric, where you still get the same result, or the result will be highly dependent on the metric that you are using.
We did not really check how robust the result is to this. So a different metric would be a way of making certain directions. So the metric which we have chosen essentially treats all directions equally, but if you choose a very different metric, you can make certain elementary transformations much more costly than others, and so they would not contribute very much. You would force them not to contribute very much. Now, I don't know how. You see that this is not so straightforward to characterize in general, because this particular choice which we've used here, which gives you this geometry of the hyperbolic half plane, for which there is a simple formula for distances. If you choose a different metric, you will not have such a formula at your disposal. So it becomes much more cumbersome to actually evaluate what you have to then calculate the geodesics and calculate the length, which is certainly doable, but it's not something which you can do very quickly.
I see.
So that's why we have not actually analyzed it, but it would be interesting to know just how robust this is. That's true.
Yeah. It's really interesting to see how, like, maybe there are some certain directions that are indeed more important than the others, like to distinguish the different phases. I mean, different.
That could also be the case. Yes, I don't know about that. I have not. It's something to look into.
Mm-hmm. Yeah. Sounds really good. Thanks. I don't know if Gaelo want to. Okay, he's going to talk about his comment.
So I had a comment related to one of the outlook points that you made, Jean-Luc.
Yes.
Which is about like trying to include the contribution from the spacetime, right?
Yes.
And like there are these. Okay, I mean these works that was done at AEI. They are motivated by ADS-CFT and what goes on the name of holographic complexity proposals.
Mm-hmm.
But basically, these are the statements that in ADS gravity, some quantities, so gravitational quantities are gravitational reflection of complexity in quantum field theory.
Yes.
But you might be tempted and try to define these sort of quantities also in cosmological spacetimes. What I'm saying is that it's a bit on a shaky footing because like we don't have like a great microscopic description of cosmological spacetime, so we don't know, like, even if the microscopic system is supposed to be quantum mechanical. But suppose that you turn a blind eye on it, then you can try to take one of these notions, which is basically maximum volume surfaces or gravitational actions in causal regions evaluated on shell, and try to take it as a contribution to complexity that comes from the background, and one can try to play this game. And well, I mean, like, I don't know it for sure, but I wouldn't be surprised if there are no works that like try to play with these ideas in the context of some Friedman, Robertson, Walker cosmologies.
Yeah, it's a bit difficult in the cosmological context because in ADS you have fixed boundaries.
Yeah.
You know exactly where to start and end your surfaces and your causal diamonds and all this. In cosmology, it's not so clear where you would even, which regions do you take? Do you plus the space-time is constantly changing.
Yeah. I mean that's true. That's absolutely true. But what I'm saying is that you can turn a blind eye on it and try to do this and see.
The question is when the eye is blind, do you still see anything, or is it or is it completely blind?
Well, I mean, like, the question is like, do you have an expectation what to see, right?
Right.
And then like you can ask if these sort of quantities reflect this expectation or perhaps not.
Yeah, I'm not. Yeah, I think it would be, like I said, I think this would be a very nice thing to try. I could not think of the right of any useful approach so far, but that of course doesn't mean much. I mean, it's
like in holography, in the context of entanglement and entropy, so a different quantity obviously than complexity. There is basically the statement that like in holography, the gravitational background is not just gravity. There are also quantum fields on top of it. It's just that for most of practical reasons, you can forget about this quantum field.
Yes.
But if you do not, then the right notion of endowment entropy in a gravitational theory is given by a sum of the semi-classical, or the sum of the classical contribution coming from some extremal surface, like Beckman's and Hawking entropy of the extremal surface. And then on top of this, there comes a correction, that is a quantum correction, that comes from a contribution from a quantum field that has entangled degrees of freedom on both sides of this extremal surface, right?
Yes.
And you might try to play the same game with complexity and say that, say, in holography, where things are a bit better under control, you can also talk about a generalized gravitational complexity in which the answer for complexity is the sum of the expression coming from the gravitational background. So this complexity equals to action, complexity equals to volume proposal, and
Yes.
quantum field contribution that comes suppressed in powers of Newton. So what, like, if one were to pursue this sort of analysis, then what you did would be like just the quantum field contribution alone.
Yes.
But on top, there would be like a more dominant contribution coming from the gravitational background.
Yeah, I think that would be very interesting. But as I said, I haven't found a good way of, a good handle on this. It's not. Well, we should discuss it some more.
Yeah, sure.
One needs a sort of a starting point for what would be a useful what would be a useful region to consider in the cosmological space-time, and what.
Mm-hmm. So one thing that one can try to do, but this is tricky, is embedding cosmologies in holography. But like to have cosmological expansion inside asymptotically anti-de Sitter space.
Right.
For some technical reasons that I don't fully recall now, it turns out to be tricky. There are works in this direction, and they were not entirely successful. Mm-hmm. There is one example I think that looks good, but this example is an example of basically two-dimensional de Sitter inside two-dimensional anti-de Sitter. So if one can take this as a point of departure, then there might be something to be done. But it's a possibility.
Yeah, it's kind of difficult. I mean, there's these also, these space times here are changing all the time, and so it's not so in ADS everything is static, and so that this is.
No, but this is not a problem for complexity, in a sense that for the holographic complexity proposals, like even if the spacetime is highly dynamical, the prescription is to find, it might be technically challenging to find the relevant, to calculate the relevant quantity in the bulk, but the prescription is clear.
Mm-hmm, mm-hmm. Yeah, the thing is that you